Okay, we're going to look at section 4.2 for this one. Okay, so the first thing we're going to do is we're going to talk about exponents. Okay, so we're starting to get into some stuff with exponents. So if you remember, we have done a to the m over n, and the top thing is our power and the bottom is our root, and we've got two ways that we can write this. We can do the nth root of a and then raise it to the power, or we can do the nth root of a with the power done first. Again, here the power is done first and then the root, and this one is the root is done first and then the power. Okay. So now what we're going to look at, okay, is normally when we have done exponents or things with exponents, okay, we've done things where the x was here and we did things like squared or cubed, or even things like 1/2 and things like that. Now what we're going to be doing is looking at something where we're going to fix the base number, and we're going to let our power kind of run around between or run through all of our values. They can be positive, they can be negative, decimals, fractions, anything like that. Okay. So one of the things that happens when we start to talk about exponentials in general, okay, is this text uses a to the x. Okay, that's going to be kind of the thing. Now, couple of things is if for any x I get a unique y value, so therefore it is going to be a one-to-one function. Okay, where if I pick an answer value, there's only one x value that's going to happen. One of the techniques that we will see here in just a little bit is if I have a to the b equals a to the c, then b has to equal c. Okay, since the bases match, the exponents have to match. Okay, if a is greater than 1, then and m is less than n, then a to the m is less than a to the m. The idea here, if you pick a base like 2, okay, and then I have, if this is, say, 3 and 4, 2 to the third is going to be less than 2 to the fourth, okay? Now, if your base, though, is between 0 and 1, so think about like a half, and m is less than n, then a to the m is actually going to be larger than a to the n, okay? So think about, again, if this was 1/2, and this was 2 and 3, so this would be 1/2 squared, which is 1/4, and then this side would be 1/2 cubed, which is an 1/8. And so that second side is smaller, okay? Now, one of the things that we also do not pick, okay, a couple of the other things that are going to happen with exponential things as we're talking here, okay, is a is going to have to be positive, okay? If we think about it, if we take something like -2 and we take it to the first, I get -2. If I take -2 and I square it, I get 4. -2 cubed gets me back to -8. -2 to the fourth gives me 16. We're ping-ponging back and forth between negative answers and positive answers, and we can't have that happen, okay? The other thing is we're not going to let a equal 1. If you notice on the previous properties, I mentioned a being bigger than 1, and I mentioned a being smaller than, or between 0 and 1, but I didn't ever get 1, and that is because if a is 1, 1 squared is 1, and 1 cubed is 1, and 1 to the anything is 1, okay? So it gets kind of boring really, really fast. So now then, if we're going to do something, let's say that we had a function like f of x equals 2 to the x. If I wanted to do something like f of -1, this would be 2 to the -1. Remember that negative exponents make things into fractions, so it's going to be 1 over 2 to the first, which is going to be 1/2. If we were going to do something like f of 3, that would be 2 cubed, which is going to be 8. Okay. Now, we can also do things like 5/2. So that's going to be 2 to the 5/2. Going back into our other stuff, that's going to be a square root of 2 to the 5th, or the square root of 2 to the 5th. Okay. Now, if you did this, we've got 2, 4, 8, 16, 32. We can draw that out a little bit. That's going to be 16 times 2. So I'd have 4 square roots of 2, okay? Now, not necessarily required unless they ask you to do it in kind of a cleaned up radical format for that one, okay? Now, if we were going to do something like f of 4.92, this is where we would have to kick in on a calculator, okay? And remember that on a calculator, in order to do this, you are going to use that little caret or wedge button. Put in 4.92, and we're getting 30.274 roughly. That is rounded. Okay. So we've got those options now. Okay. Now, next thing, okay, is when we talk about a function, okay, so we're going to define f of x to be a to the x, okay. Now, again, things that have to happen here, a has to be greater than 0, a cannot be 1, okay. X is allowed to be anything that it wants to be. Now, these exponentials fall into one of two categories, okay? We're going to look at when a is greater than 1, and we're going to look at when a is between 0 and 1, okay? So we are going to start with the greater than 1 version, okay? So we're going to look at f of x is a to the x when a is greater than 1. Now, when we talk about graphing stuff, key points that we are going to use, okay? We're going to use the point 0, 1 because anything to the 0 power is 1, okay? As long as it's not 0, okay? So no matter what this number is, if it was a 2, a 3, a 5, 4.2, anything like that, to the 0 power is automatically 1. Now, the other spot that I'm going to use is 1 comma a. And that is because anything to the first power is itself. So I'm going to have 1. And then I'm going to come up here and say that this is a. I don't know where that is. It may be at 2. It may be at 3. It may be at 5. Okay. So what happens here is this graph goes up this way, and it's going to taper tail back along this direction. Okay. Now, we do have one of those I'm not touching you lines across that horizontal x-axis. Okay. So a couple of things we've got here. Our domain is going to be all real numbers. Our range is going to be 0 to infinity. Okay. Again, open-ended on the 0 there. Okay. As far as increasing, it's always increasing. It's never decreasing on this particular one. Okay. We are also continuous on our entire domain. Okay. Now, we do have a horizontal asymptote at y equals 0. Okay. And like I said, we've got these two key points. Okay. So now, if we take a look, and I'm just going to erase a couple of parts of this. Okay. If we now look at being between 0 and 1, again, I'm going to use the point 0, 1. But now A is going to be someplace down here. And so what's going to happen is this graph is going to go this way. And again, we've still got that same horizontal asymptote. Now, the domain is still all reals. The range is still 0 to infinity. But this time, instead of increasing on the entire domain, it's decreasing on the entire domain. It is still continuous on the entire thing. And we still have that horizontal asymptote at y equals 0. Okay. Now then, when we start to do graphing stuff with this, okay. Now, when I do graphing stuff, I'm going to focus on these two key points and that horizontal asymptote. Okay, so that's what we're going to be focusing on when we do this. Okay, so first off, okay, and we need to have a little bit of a talk here. Okay, personally, I don't like this notationing. Okay, because it's really difficult to tell where the negative kicks in. Okay, does it mean to be part of the 2? If so, then that's a negative base, and that's not allowed. Or is it meant to be out in front? Personally, what I like to do with this is write it with a set of parentheses so that you know the negative is out in the front. Now, with that negative out in the front, we know that this flips over the x-axis, okay? It is that vertical kind of up and over type of notationing. So, I'm going to do this with a couple of colors here. So, first off, key points, and I'm going to mark these with little x's, okay? So, I've got the point 0, 1, and then 1a. My a is 2, so I'm going to put that mark there. Now, the other thing that I know is I have that horizontal asymptote sitting right there. So now, these need to flip over the x-axis, okay? So if this one is up 1 over the x-axis, when I come down here, here's where it's going to be on my graph. This one is 2 above my x-axis, so now it's going to be 2 below my x-axis. When that asymptote flips over, it's going to stay right where it was. So now I have a graph shape that looks like this. Okay. Now, domain for this is still going to be all reals. Range for this, though, is going to be negative infinity to 0 because it did flip over the x-axis. Okay. So you've got to kind of be watchful of that. Okay. So now then, let's take a look at another one. So we'll look at okay. Now, sometimes what can be helpful, okay, to help remember about what's going on here is you may want to put a set of parentheses around here just to help you remember that it's with the x, so it's going to do the opposite of what you think. So +3 is actually going to go left 3. So here we go again with our grid space. Again, I'm going to mark in just x's. Okay, so here is the one here, and then again, we're at a base of 2, so I'm going to go to 1, 2. So now I'm going to move these left 3 spots. So I'm going to go 1, 2, 3 to the left, and 1, 2, 3 to the left. That asymptote, when it moves, 1, 2, 3 to the left, actually stays right on top of the same line that it was on before. This is going to go up and over. Okay. So again, domain is going to be all reals. That hasn't changed. Range, we're on 0 to infinity. Do make sure that on those ranges you are working low to high when that happens, okay? So, now, one more, just so we can kind of get a little bit of everything in here. And again, helpful hint, just to help you remember that that stuff is up there in that exponent, okay? So that's going to go right 2, down 1. So here we go to our grid space. We're again putting 0, 1 and 1, 2. Okay. And we're going to go right 2, 1, 2, down 1. I'm going to go right 2 and down 1. Now, asymptote was here, right 2, down 1. Okay, so this one we're actually going to have to look and see that asymptote is in a new location. So this is going to arch up and down. Now, helpful hint, okay, domain for this is still all reals. The range, that asymptote is going to help you figure out your range. That asymptote's at -1, so we're going to stay just above that value, and then we're going up towards infinity, okay? Now, helpful hint here, if you had been doing, okay, let's say that this had been 3 to the x minus 2 minus 1, I still would have had this marker spot right here, but I would have been at 1, 3, okay? So I would have been using this one and this dot up here, or this X marker up there, if that was a base of 3. Okay, so now let's take a look at solving some exponential equation stuff. Okay, now then, I'm going to start with something kind of simple. Okay, so we're going to have something like 2 to the x equals 16. Okay, so what we've got to do here, and this goes back to that whole idea of a to the b equals a to the c, means b equals c. Okay, so that's where we're kind of going here. So in order to make this happen, we've got to make sure that they get into the same base. Okay, so you're never going to take smaller numbers up to larger ones. You're going to have to take large ones and bring them back down. So we're going to have 2 to the x equals 2 to the 4th. Okay, so 2, 4, 8, 16. Now the 2's can go away, so I've got x equals 4. So there's our answer for that one. Okay, so we'll take a look at another one. All right, now you may be looking at this going, what the heck? Okay, keep in mind, first off, we're going from a fraction to a whole number. Okay, if you're going from fraction to whole number or whole number to fraction, that means that that x is going to wind up being negative. Okay, so we automatically know that when I get ready to do this, I'm going to wind up having 1/3, and it's going to have a negative exponent up here. Okay, so now what I really need to focus on is 3 getting up to 81. So 3, 9, 27, 81. So it's going to be a 4 up there. Again, the 1/3 will cross each other off. So we've got x is -4. Okay. So we've got those two now. Okay, so taking a look at another one. Okay, now with this one, it's a little bit, we now have x's on both sides. Okay, so now again, we're going to have to bring the 8 down. So this 2 to the x plus 4 isn't going to change. Now, the 8 can be rewritten as 2 cubed. Anything that was up in that set of parentheses, or up in that exponent, needs to get written in a set of parentheses. So now the bases of 2 can go away. So I'm going to have x plus 4 equals 3. And then I have that x minus 6. I'm going to distribute. I'm going to move this x over. I'm going to subtract it. I'm going to add my 18. And then we'll divide by 2. So I've got x equals 11. Okay. Now then, one other one, okay, and this just kind of hints back to the beginning of this that we talked about. Okay. When we have something like this, is that in order to get rid of those fraction exponents, okay, you're going to flip that power over. Okay, because that's going to be how we clear those up. The idea here is powers raised to powers multiply. Okay, so you're going to have 4 times 3, which is 12, 3 times 4, which is 12. So you got 12 over 12, which is 1. So that's just going to give me an x. Now, over here, we need to handle this. So 4th root of 81, I'm going to try and work with that first, and then cube. Now, 4th root is an even root, which means we've got to consider both the plus and the minus version of this, okay? So thinking about this, I'm going to have plus or minus, and considering the problem that we just did just a little bit ago, that's going to be 3. So I'm going to have x is 3 cubed, and x is -3 cubed, okay? So 3 cubed is 27. -3 cubed is -27. So we've actually got 2 answers here, okay, for this particular problem. Okay. Now, the next thing that we're going to look at is an application of our exponential stuff, okay? So what we're now going to look at is compound interest. And our formula looks like this. Okay. A is the amount that's in the account when we're all done. P is the principal. Okay, and that's the amount that you put in the account to start with. R is your rate, and that does need to be in decimal. N is your compoundings. Okay, that is how many times a year you get your interest. Now they're going to use words like quarterly, monthly, semi-annually, things like that. And that's going to tell you how many compoundings in a year that you get. And then T is going to be our time. And this is generally in years, okay, when we do this. So we're going to take a look at one of these. I'm going to leave our formula up here, okay, at the top end. So what we have is $1,000 deposited. We've got 4% quarterly, and they want us to do 10 years. Okay, so plugging that in. Okay. And I'm going to do a little bit of cleanup here. So I've got 1,000 up here at the front. 0.4 divided by 4 is 0.01. So we've got 1.01, and that's going to be the 40th power. Okay, and then this is going to go straight into a calculator. So 1,000, 1.01 raised to the 40th. And we're going to do 2 decimal places because we are talking about money. So we're at 14.88 and 86 cents. Okay, now if they ask you the interest, okay, so if they ask you how much interest is the amount that is over the original deposited amount. Okay, so they put $1,000 in the account. That means we had $488.86 in interest. Okay, that is the extra amount that ends up in the account after it's said and done. Okay, now sometimes, okay, they will ask the question, okay, we need $6,000, okay, in 5 years. They want us to figure out how much we need to put in now if we're going to get 3.1% annually. Okay, and they mentioned nothing about compoundings here, so we're going with it is compounded once. Okay, so one time. So in this case, we're going to put 6,000 in over here on this, and we're looking for P, the amount that we're going to be putting in the count. So 1 plus 0.031. Do be careful with that. 1, and then we've got 1 times 5. So again, I'm going to do a little bit of cleanup here. To the 5. What's up, puppy? Okay. So now, what we're now going to do, okay, and guys, with this, I am going to let my calculator, now I'm going to write just part of this on here, okay, but I'm going to let my calculator use this full number. So I'm going to do 6,000 divided by that previous answer, and we get 5150.60 equals P. Okay, so that tells us how much, and again, we just divided that back under to the other side. Okay, now with this same setup, okay, still needing 6,000. Okay, but they go, we only have 5,000 to put in. What kind of interest rate do we need? And again, this is still over the 5-year period. So we're going to do 6,000 going to be 5,000. Okay. Now, R over 1 times 5. Okay. So again, I'm going to do a little bit of cleanup here. 1 plus R to the 5th. Okay. I'm going to divide that 5,000 back over across. So I've got 1.2 equals 1 plus R to the 5th. Okay. Now, in order to get rid of that 5th power, we're going to do a 5th root on both sides. Okay. Clean that up. So the 5th root. Now, guys, in order to do that, okay, you need to go to, you need to put a 5 on your screen first. So I'll bring this under here. So I'm going to put 5 on my screen. I'm going to hit math. And then I'm going to go down here to option number 5. That now makes that a 5th root. And I can put in the 1.2. Okay. So I get 1.0371 equals 1 plus R. So R is going to be this 0.0371. We'll go with that. And then if I bump to, if they want it in percentage, okay, we'll just bump that decimal over and get 3.71%. Okay. Now, there was a mathematician, okay, that started playing around with an equation, okay. He started to play around with 1 plus 1 over n to the n, okay. Now, some of this may look a little bit familiar, okay. This used to be an R and a T, and he was doing this work separately, okay, and he wasn't focusing on the compound interest. He was just playing with this. And so he was interested in what happens when you let n get really, really large. So if we start off with saying something like n is 2, so we'd have 1 plus a half squared. And then we go to 1 plus a third cubed. And then 1 plus a fourth to the 4th. And what he realized, as n really big, okay, this whole thing starts to turn into 2.7182818284, and it keeps going, okay? This is one of those, it doesn't ever stop, okay? And it doesn't ever repeat. Now, other mathematicians realized that this was a really great thing to use, and it had a lot of applications in it. So they named it after the mathematician that it came up with. His name started with an E, so this is now designated as E. And when you look on a calculator, okay, specifically down here, we have like an E to the X right above here. We also have an E over here kind of underneath where you would get pi, okay? This is the number that it uses for that, okay? The guy's name, and with everything in my East Texanness, okay, I want to call that Euler, okay, similar to Euless, Texas, but it is not. This is Euler, okay. He was European, maybe Swiss, I think, and so it is pronounced Euler. Now, one of the things that can happen, okay, thinking back to our compound interest formula, if you can get what's called continuous compounding, okay, meaning you're not getting it quarterly, you're not getting it monthly, you're not getting it weekly or daily or hourly or minute or second, okay, it's just sitting there perpetuating a cycle, then the formula shifts to PE to the RT. Okay. So now, let's go back and talk about that problem, okay, that we had from the original one, okay. It was that $1,000, okay, for 10 years. And now let's say we got continuous interest, okay. What that's now going to look like and we were getting 4%, okay? So this would be 0.04 times 10, okay? And again, I'm going to clean this up just a little bit. It's going to be 0.4 up there. So we're going to do 1,000 e to the 0.4, and we're going to get that that is 1491.82. Okay, so it is higher than what we got before. Now, sometimes what we see happen is they will want you to compare investments, okay? And so what they may do is they may have done a problem like this, but instead of getting 4%, they may have done something like 3.8%. And they're going to ask you at 5 years, which is the better investment, or at 10 years. It is not always the case that one is always going to be better than the other, okay? It may be that early on, one investment is better, but later on, the other investment gets better, okay? So you've got to kind of watch what's happening with those, okay? Now, one other thing that we need to discuss in this, okay, is what's called exponential modeling. Now, exponential models follow the form, okay? Y equals y naught e to the kt, okay? Y here is your amount. Y naught is the original amount. K is your rate, okay? Now, one kind of neat thing to know about this, if K is positive, then it's growing or getting bigger. If K is negative, it's what's called decaying or getting smaller, okay? And then T is time, okay? Now, it doesn't always have to be in years, just so long as they are specific with it when they do this, okay? So one of the things that they discuss with us, okay, is they talk about, and they gave a table for this, and we'll talk more in a little bit about how they came up with this equation. But they're talking about the amount of carbon dioxide in the atmosphere, okay? And so the equation that they come up with sorry, 609, and they use the letter X here. They could also use the letter T. And with this, they specify okay, so basically what they're doing is they're saying that this model's from 1990 to 2275. And if they wanted us to figure out the amount of carbon dioxide for any particular year, they would ask us to plug this in. Now, if they ask you to do something like double or triple an amount, okay? So if they ask you to double or triple like 208, okay? So the double amount would be 560. The triple amount would be 840. Okay. Now, what we would do is on our calculator, okay, for right now, the way that we would do this is we would put this equation in Y1. Okay, so this would go in Y1. This other value would go in Y2. So what you would have is a graph that does like this, and then you would have another line passing across at it, either at 560 or 840 or whatever the number is. And then you're going to do that second trace and the intersection, and you're going to get where that intersection point is. Now, do keep in mind with this that you have to make sure that the calculator can see the intersection for it to actually be able to find it, okay? So I hope this helps explain this loveliness. And I will get some other stuff uploaded for you guys.